Okay, we'll get started. What we'll do, we'll finish a few more topics before we go to the review. Okay. We we discussed till this point last class about doing orthogonal projection onto a subspace spanned by a single vector. That means a one-dimensional subspace. Right? And we saw that that operation, the orthogonal projection operation, can be represented by a matrix multiplication operation, which is given by shown by A, which is essentially A transpose, where and divided by A transpose A, where A is a vector that's whose span is this one-dimensional subspace that we are interested in. Right? Now, before we proceed, um, if you look at this equation, right? This is the equation for the projection matrix. It's got A transpose divided by A transpose A. The denominator is a scalar. What is that equal to? Inner product of a vector with itself. What is it equal to? Yes, you should know this by now. The square of the second norm. Okay? That means if you write it like that, if you replace the denominator, square of the second norm, there are two terms, right? It's a square of the Euclidean norm. You can separate that out, and then let's say we write it like this. You can write it like this. Right? So, because this is a vector multiplied by a scalar, and we are taking the transpose, we can write the whole thing as A divided by this is also another vector, simply scaled version of A, and let's say we call that A cap. What is special about A cap? I'm writing A cap as well, A cap is normalized, right? The two norm of A cap would be 1. So it looks like, so the projection matrix is simply, so if you want to project onto a one-dimensional subspace, if we take a vector from that subspace which has length 1, Euclidean length 1, right? And if we simply take the outer product of that normalized vector, you get the projection matrix. Okay? And in fact, if it's not, if the vector that you've taken is not of unit length, you have to have this denominator term, which is essentially you accounting for the fact that the vector is not of length 1. So the main thing to remember is if you want to project onto a one-dimensional subspace, you simply take a vector of length 1, Euclidean length 1 from that subspace, and you do the outer product, you get get the orthogonal projection matrix. Okay? Let's do an example. Let's say we're talking about a subspace which is spanned by that's the subspace onto which we want to project. Okay? What is the projection matrix for this subspace? Orthogonal projection matrix onto this subspace. let's say the vector we are talking about is simply this. Yep. One is it? No, orthogonal projection matrix, P. How do you, okay. The orthogonal projection matrix is given by A transpose by A transpose A, which will be 1 minus 1. A transpose A will be 2. So this will be 1 by 2, 1 minus 1, minus 1, 1. Okay. Well, this, does A have length 1? Is it normalized? It does not have Euclidean norm 1, no? The Euclidean norm is 2. So if we normalize it, then we simply have to divide it by square root of A transpose A. This is the formula if you have a non-normalized vector. But since A cap is normalized, the denominator will simply be 1. So if you do A cap transpose, you'll still get the same thing. Right? Well, obviously, because A cap was derived from this expression. Okay, right. Now, let's say we want to project a vector 2, 1 onto this orthogonal, onto this, we want to do the orthogonal projection onto this subspace. What would be P, small p? Well, small p would simply be this. What would you get? So there'll be I'll take the half outside. Tell me what you will get. Yeah. Sorry. Guys, come on. It's matrix multiplied by a vector. So it'll be 1 minus 1. 1 multiplied by 2, 1 will be half. So 1. So it looks like we get this. Okay. That's the projection, right? Now, this is my subspace. That is the span of, sorry, that's wrong. Right? My vector 2, 1 is 2. This is my vector B. This was A. And when we did the orthogonal projection, we found that we actually got something like this. This was P. Now, the orthogonal projection of B onto the subspace, onto this subspace S, is just this vector P that I've drawn here. But if you see how we derived our projection matrix, right? We used a particular vector A from the subspace, that is this vector. Well, somebody could say, well, what if I choose this vector? Why should I choose only 1, 1? You're talking about projecting onto a subspace. And we've chosen one particular vector from the subspace to compute the projection orthogonal projection matrix. Somebody else could ask, well, what is so special about that vector? What if you used a different vector? Okay. For example, what if I had used, let's say I'm going to call it C, and this is C. All vectors from the subspace will be of the form alpha minus alpha. So I could choose another vector. Let's say it's minus 4, 4. Right? This is a vector from that subspace, from this subspace. Right? What will happen if you compute the orthogonal projection matrix using this? Let's compute it. So P will again be C transpose divided by, since C is not normalized, tell me what you get. What is C transpose C first? What is C transpose C? That will be 32. Now, if you do the numerator, it will be minus 4, 4 multiplied by minus 4, 4 divided by 32. It will be 1 by 32. The first term will be 16. Second term will be minus 16. Third term is minus 16, and this will be 16. Right? Now, if you take the 16 out from the matrix, then you will get 16 by 32 divided into 1 minus 1 minus 1, 1, which is nothing but half. Right? The projection matrix, the orthogonal projection matrix onto the subspace that we computed when we chose the a vector A was half 1 minus 1 minus 1, 1. If you choose another vector from the same subspace and you compute the orthogonal projection matrix, you get the same value, which makes sense, right? The subspace is the same, right? So the orthogonal geometric operation that I do is the same. Whether I choose C or A from the subspace to compute my orthogonal projection matrix should not change, and that's what you find. So the orthogonal projection matrix is independent of what vector you use from the subspace to compute your orthogonal projection matrix. Okay, so what we've seen so far is simply an orthogonal projection operation onto a one-dimensional subspace. Now you could ask, well, what is so special about one-dimensional subspace? What if I wanted to do, so what if I did not want to project to a line passing through the origin, but a plane passing through the origin, a two-dimensional subspace or higher dimensional subspaces? So it turns out you can easily extend this. Okay? So this, we can project vectors onto higher dimensional subspaces, but to be able to do that projection, in the one-dimensional case, what did you need? Well, you needed a vector from the subspace which is non-zero. Okay? And we said if you have a vector from that subspace which is normalized, which has Euclidean length 1, then the orthogonal projection matrix is simply this, the outer product of that vector with itself. Now, a simple extension of this is if you have higher dimensional subspaces, what we need to be able to find the projection matrix corresponding to an orthogonal projection onto a high dimensional subspace is essentially a basis for the subspace. So in fact, if you look at the previous example, when I said if you have a one-dimensional subspace and you have a non-zero vector from that subspace, that vector is essentially a basis for that subspace. Right? Basis is linearly independent. It's not zero, so it's linearly independent. And it will span, because it's from the one-dimensional subspace, it will span that subspace. the extension of that to higher dimensions is if you want to project onto, if you want to do orthogonal projection onto a higher dimensional subspace, what you need is a basis for that subspace. That means if I have a m dimensional subspace, I need a set of m vectors which are linearly independent and which will span that m dimensional subspace. If I have that, and if that basis is an orthonormal basis, okay, what does an orthonormal basis mean? So, for example, let's say I give you a set of vectors u1, u2, ur, and I say this is a orthonormal basis for a r dimensional subspace. What do you understand by that? By this statement? What is an orthonormal basis? The orthonormal basis is where the length of all the second norm of all the vectors are 1 and all the vectors are mutually perpendicular to each other. So if you want to find the orthogonal projection matrix onto a r-dimensional subspace, what you really need is an orthonormal basis for that subspace. If you have an orthonormal basis for that subspace, then it turns out that the expression for the projection matrix is actually quite simple. Let's say this is an orthonormal basis for the r-dimensional subspace, and let's say I form a matrix U, which is essentially where I essentially concatenate the columns together like this. I've essentially written the matrix in a block row form, where each of the ui's is a column vector, which is one of the basis vector from this orthonormal basis that I have for my r-dimensional subspace. Once you form this matrix U, it turns out that the projection matrix is fairly simple. You take U transpose, and that is your, and that matrix that you get will do the geometric operation of, if you take the matrix and multiply it by a vector b, and let's say the plane that I'm talking about is this plane, and let's say the vector is sticking out here, that operation pb, algebraic operation, will correspond to a geometric operation where you go to the tip of the vector b, you drop a perpendicular from the tip to the plane, and wherever that perpendicular line meets the plane, that point is the end of the projected vector p. Now, if you look at the one-dimensional case, right? The one-dimensional case is essentially a special case of this, right? If you have a normalized vector for a one-dimensional space, if you take a normalized vector, right? That vector is essentially an orthonormal basis for that for one-dimensional subspace. Right? If that is the case, then the way we found out the projection matrix was A transpose, which is equivalent to saying, which is exactly this. It's just this is a more generalized form. If R was 1, these two equations would be exactly the same. Okay? Now, maybe let's do an example, and then we'll look at other things. Let's say we're talking about orthogonal projection onto two-dimensional subspace in 3D, right? So then let's say we have two vectors. One, Are they orthogonal? Are the two vectors orthogonal? I'm essentially asking, is U1 transpose? Yeah, they're orthogonal. Okay. Are they? So if I form a set like this, can I say that's an orthonormal basis for this for the subspace spanned by these two vectors? They're orthogonal. That means they're linearly independent. So can I say that these two U1 and U2 form a orthonormal basis for the subspace that they span? Oh, you don't have to think so much. What is the condition for an orthonormal basis? They should be mutually perpendicular and should have Euclidean distance one, a norm one. Is the Euclidean norm one for each of these vectors? Okay. If it's not, how will you make them one? Okay, tell me what the normalizing factor is for the vectors. No? All right. What is the square of the Euclidean norm of U1? It's U1 transpose U1, which is which is square. That means the Euclidean norm, if you're not sure that these still have length 1, to do this, you do it again. So I'm going to you now compute the Euclidean distance or compute the inner product of each of these vectors with itself. If you take the inner product of each of these vectors with itself, it will be 1 by root 6, 1, 2, 1, and multiplied by 1 by root 6, 1, 2, 1. The scalars will come out. You're left with 1 to 1, 1 to 1. We've already computed this. That's 6. So 6 by 6 is 1. So they do have length 1. Okay. Okay. So the original vectors did not form an orthonormal basis, but these two vectors form an orthonormal basis. Right? Now, if you want to find the orthogonal projection matrix onto this subspace, then you first form the matrix U, where the first column is U1, second column is U2, and the orthogonal. Let's write that down anyway. So that will be what? 1 by root 6, 2 by root 6, 1 by root 6. That's u1. And then you have 1 by root 3 minus 1 by root 3, 1 by root 3. That's your u. Now the orthogonal projection matrix is given by u transpose. That will be 1 by root 6, 1 by root 3, 2 by root 6, minus 1 by root 3, 1 by root 3. That's u. U transpose will be simply the transpose of this matrix. That means it will be 1 by root 6, 2 by root 6, 1 by root 6, by root 3. If you multiply these out, what will be the shape of the matrix that you get if you multiply these two? Sure. Okay. What will be the first element? Okay. You sure? What will the first element be? One by three, is it? By three? Can you verify? It won't be 1 by 2. That's for sure. 1 by 3. Yes. 3 by no. It'll be 4 by 6. No, sorry. 3 by 6. 1 by 2. Yeah. Okay. Ah, yeah. Sorry. I'm sorry. You're right. Yes. 1 by 2. Yes. Okay. What about the next one? Can you compute the other ones and tell me, please? It should be 0. It'll be 2 by 6 minus 1 by 3. It'll be 0. Third one will be 1 by 6 plus 1 by 3. That will be 1 by 2. This will be 2 by 6 minus 0. What will this be? 4 by 6 plus 1 by 3. That's 2 by 3. That's 1. 2 by 6 minus 1 by 3. 1 by 3 is 0. Okay. That will be our orthogonal projection matrix onto the subspace spanned by these two vectors. Okay. We would have obtained the same matrix if we had chosen some other set of vectors, two other vectors, which formed an orthonormal basis for this subspace that we started with. You'll get the same matrix. Okay. Before we proceed, is the projection matrix symmetric? Don't look at this. Maybe here it turned out to be symmetric by chance. Okay. How? If yes, you'll have to explain why. If it's no, you'll have to give me a counter exam. Sorry? No. Here, Adarsh, listen to what I'm saying. I said, yes, this has come out to be symmetric. That could be by chance. It does not mean it's always symmetric. Okay. So I'm asking you, if you say that, so my question is general. Are projection matrices, I've looked at this. Let's look at some of the previous examples that we did. Here, the two-dimensional case, it was symmetric. Maybe we did others before. You did not? Yeah. Here. This is also symmetric. So the three projection matrices we've computed look symmetric. Then you might be tempted to hypothesize, oh, maybe all projection matrices are symmetric. Okay. So my question is, are all projection matrices symmetric? Given that we know projection matrices are computed like this. What is the condition for a matrix to be symmetric? Sorry? A equals A transpose, right? So if P is symmetric, then P should be equal to P transpose. But we know what is P? P is U transpose. We know P is U transpose, full transpose. What will happen if you take the transpose operation inside? Sorry? So it will be, what will be the first term? Just U transpose, is it? If you have AB and you do the transpose, what do you get? The transpose, right? That means this is A, U transpose is B. So it's not U transpose. It's U transpose whole transpose, U transpose. What is transpose of a transpose? It's the original matrix. That means this is there. P is equal to P transpose. That means it's not a coincidence that the three matrices that we computed turned out to be symmetric. Orthogonal projection matrices are always symmetric. Okay. Now we have U transpose. Let's take a simple case. Okay. Let's take the one-dimensional case, right? Let's say that means the U matrix is simply U1. Okay. What will happen if you compute P square? If U is simply U1, then P is simply U1 transpose. Okay. So what will happen if you compute P square? Well, P square is P into P. P is U1 transpose. U1 transpose. Can we simplify this any further? Well, let's get rid of the parentheses or move the parentheses around. So remember, if I told you, if you have a whole bunch of matrices that are multiplied together, look for a grouping that will give you a scalar. If it's a scalar, you can pull it out. Yeah, is there a scalar here? Let's write it down. U1 transpose, U1 transpose. Is there a scalar here somewhere? Yes, here. If you group these together, that's a scalar. But we know that already. What is U1 transpose U1? Well, it's 1 because we're it's an orthonormal basis for a one-dimensional subspace. If it's 1, that means what I get is simply U1 transpose. That means if I do P square, I get P. What if I did P cube? What will I get? Yep. 1, is it? Are you sure? Why is it 1? Huh? Why? Yes. Yes, it's simple. This is P into P square. P square. P square is P. So that's P into P. P square is P. So any power of orthogonal projection matrix is the projection matrix itself. And whenever you have a situation like this, where P square is P, again, just a term to remember, these are called idempotent matrices. See, but we associated a geometry with orthogonal projection matrix P, right? What was the geometry? Let's say we're talking about, let's say this is a one-dimensional subspace. You have any vector, some vector B. The orthogonal projection, the geometric operation is you drop a perpendicular, and then wherever this meets here, that is the vector P, and this vector P is obtained by multiplying B by the orthogonal projection matrix. So this operation of dropping a perpendicular and finding where it intersects, that is essentially what is represented by the matrix P. What is the geometric operation represented by the matrix P square? Well, it's P into B. Well, I know what this operation is, right? That means I know what the second operation is because I'm repeating the same operation again and again. So if I take B, I drop an orthogonal to the subspace, find the vector, find the point of intersection and find the vector P. And then I repeat the same thing to this vector P, because if this will come out to be P times P. Okay. If I orthogonally project P onto the subspace, onto this black colored subspace, what will I get? P is already in the subspace. If I do the orthogonal projection, I'll get the same vector again. We saw this example earlier. Okay. So P square is essentially repeating this orthogonal projection operation 2 times. So P power n will be repeating the same operation again and again. And it makes sense that P square is P because once you project to the subspace, once you're in the subspace, if you any repeated projection operation will give you the same vector. That's why P square is P, because the first P will take you to the subspace, the other P's don't do anything because you're already in the subspace. Right? And as we discussed earlier, let's say we have a subspace S, and let's say we have two orthonormal bases. So here I've written the basis in the matrix form. Okay, so I'm going to call this V1. So U1 simply means it's an orthonormal basis like this, and V1 simply means these vectors here form an orthonormal basis for the subspace S. These vectors here form an orthonormal basis for the same subspace S. They're two different bases, orthonormal bases. Now, if you use U1 transpose, we will find that will always be equal to V1 transpose. So it doesn't matter what orthonormal basis you choose for your subspace. As long as you're talking about the same subspace, the projection matrix will come out to be the same. Okay? That's what I've written here. Don't worry about the C, but that's what I've written here. The orthogonal projection matrices will be the same. Okay? All right. Now we come to another important idea. So we've already seen what are complementary subspaces, right? What are complementary subspaces? In words. Should be able to say it in words. Well, complementary subspaces are subspaces such that if you add the two subspaces, you get the original parent space, and their intersection is zero. Is only the zero element. There is nothing common in between them. Okay? So it turns out that if you have complementary subspaces like this, and let's say we have some vector here. Let's say V. Right? And let's say we have two complementary subspaces. This is my X. This is my Y. These are two complementary subspaces of R2. Because if I add these two, I will get all of R, and the only point where they intersect is 0. Let's say now I have a vector V. Okay. It turns out that if you have complementary subspaces, you can always write any vector from your original parent space. So here, I'm going to make it more explicit. Our subspaces of R2, and this vector V belongs to R2. Okay? So when you have a, and we know, no, not, no. Those are subspaces, not vectors. Okay? Complementary subspaces, and we have some vector V which is in R2. Turns out that any vector, we can write it as a sum of, if you have two complementary subspaces like this, you can write it as this a sum of two vectors. Okay? Vx and Vy. Okay? Vx and Vy will be vector, and here, this vector Vx will belong to the subspace X. This vector Vy will belong to the subspace Y. And if you add these two vectors, you will get V. Okay? And these two vectors, Vx and Vy, are called, or Vx is called the component of V in X, in the subspace X, and this is called component of V in. Okay? That means if you have two or complementary subspaces, and if you give me any vector, I can write it as a sum of a component from each of the two complementary subspaces. Okay? Okay? We don't have to restrict ourselves to only two. If you think of R3, let's say I get three subspaces which are complementary. If you give me any vector, I can write that vector as a sum of three components, one coming from each of the three complementary subspaces. Here, in the two-dimensional case, let's look at what those components will be. So we need to take a vector from X and vector from Y, so that when we add them, we should get V. Right? So it will turn out that if you take any element from X and Y, right, if you add them together, the parallelogram law of vectors apply, right? That means if I take Vx, I move along the X subspace by Vx, and then from the tip of Vx, I move in a direction parallel to the Y subspace by Vy, and that will be the sum of the two elements, right? Right? That means I need to find a path of moving along X and then parallelly to Y, so that I reach this tip. Or since addition is commutative, I can move along Y first and then move parallel to X to get to that point. So that will be this. That means I need to move by so much distance along X. That means this must be Vx, and this is how much I'm moving along parallel to Y. That means this must be Y. This is if you have two, right? In fact, in the case of R2, you can only have two complementary subspaces. If you add a third one, it will turn out that they won't be complements. Okay. Now, if you have R3, right, let's say we have three complementary one-dimensional subspaces. You can similarly write your vector V as a sum of and in fact, if the three subspaces are one-dimensional, what if I have two complementary subspaces in R3, where one is a plane, the other is a line? Okay? Then I would only have two components. A component on the one-dimensional subspace and a component on the two-dimensional subspace. So the point I'm trying to make is you can have multiple complementary subspaces, and any vector uh, from your original parent space can be written as a sum of components from each of the complementary subspaces that you have. Okay? It just turns out that if your subspaces X and Y are orthogonal complements, okay, if they're orthogonal complements, then of course we know one more thing. We know that Vx will be perpendicular to Vy because the subspaces are perpendicular. When two subspaces are perpendicular to each other, that means any vector you choose from one of the subspaces will be orthogonal to every other vector that you can choose from the other subspace. Since Vx is from X, Vy is from Y, they have to be orthogonal. That means and when you have orthogonal complements, then the components are called orthogonal components of the vector. X and Y are the orthogonal components. Okay, and it's quite easy to find the orthogonal components. Okay? So if X and Y were orthogonal, right? Why? They're orthogonal. If I have a vector V, if I apply the parallelogram law of addition of vectors, right? That means my X, I have to move along X direction by so much, and then move along Y by so much. That means my Vx has to be this, and Vy but if you look at this, Vx is simply the orthogonal projection of V onto the subspace X. Similarly, Vy is the orthogonal projection of V onto the subspace Y. So if you have a basis for Y, you can find out Vy. If you have a basis for X, you can find out X. How? Let's say I have X, and I say this is an orthonormal basis for the X subspace. Well, I simply find the orthogonal projection matrix onto the subspace X, which is simply X transpose. Similarly, if I have an orthonormal basis for Y, then Y transpose will give me the orthogonal projection matrix onto the subspace Y. That means Vx will be Vx into V. Sorry. And Vy will be okay. Okay. Now we go back to the four fundamental subspaces. If you remember the four, what are the four fundamental subspaces? Yes. So the column space of A, the the row space of A, null space of A, left null space of A. Okay? And if the matrix A has rank R, and let's say A belongs to n cross M, what can we say about the dimensions of these subspaces? What is the dimension of the column space and the row space? No, the dimension of the column space. See, these two will belong to Rn. These two will belong to Rm. The row space and the column space will have dimension R. This will have n minus R. This will be m minus R. Okay. This is what we saw earlier. Now that we've talked about orthogonal subspaces and all that, it turns out there is one more interesting property relationship between them. It turns out that the column space and the left null space, which are subspaces of Rn, are orthogonal complements. It means the column space of A is perpendicular to the left null space. And if you add them together, if you add the two subspaces together, you get the original pair in subspace. Similarly, the row space and the null space are orthogonal complements. I'm going to skip this for now. So earlier, if you remember, we drew a picture like this. This is the picture I had drawn. Right? I said if this is the column space, this is the this is the row space, and this is the column space, and this will be the left null space, and this will be the null space. In fact, that picture is not very useful. Or well, it's useful, but it's not complete. The actual picture should probably be something like this. This is your input space, output space. This is your column space. Okay. And this particular visualization here simply emphasizes that the left null space is orthogonal to the column space. Similarly, the row space is orthogonal to now. If you take any vector x from Rm, we've got we've got two complementary subspaces. In fact, we've got two orthogonal complements: the row space and the null space. We earlier saw that if you have any vector and if you have complementary subspaces, you can write that vector as a sum of components from each of the complementary subspaces. Because we have orthogonal complements here, that means I can write x as a sum of two components, one called xr and one called xn. Xr is the component of the vector x from the row space of A. Xn is the component of x from the null space of A. If you add them together, you get the original vector x. Okay. Now, if you apply the matrix A to x, right, you'll get, let's say, some y or some b. Okay. But what is x? X can be written as xr plus xn. Okay. If I multiply it inside, I get xr plus a times xn. Okay, so that's what I've written here. So this is your original vector x. Let's say this is your original vector x. This point is the origin of Rm. It has two components. One, it has this xr component, and the xn component. If you add them together, you get your original vector x. Okay. Turns out that this vector, so we can ask what happens to both of these, right? Because xn is from the null space, a times xn has to be 0, because that's the definition of an element from the null space, that it gets mapped to 0. That means this is equal to 0. So that's why I've drawn here. This point here under the transformation A gets mapped to the origin here, 0. That's the dashed blue line. Okay. And this is equal to B, which means XR must get mapped to B, right? Because A times X is B. That's this. That's A times X is B. Because this goes to 0, this has to be B. Okay. So effectively, when you do AX, okay, let's say the matrix A has a non-zero null space. That means what gets mapped to some non-zero vector B is only the component of X that is in the row space. Whatever component it has in the null space gets nullified to 0. Okay. Okay. And no matter what element you choose from here, okay, this entire portion of Rm gets mapped to 0, and this entire portion gets mapped to this portion. That means no matter what element you choose here, you can never get anything in the left null space. That means when you do AX, right, what comes out will always be only in the column space. It means it will not have a component in the left null space. It's restricted to that column space of A. Okay. And in terms of solving AX equals B, let's say we have AX equals B. Let's say we know B, we know of course A. And we ask, okay, can you solve for X? If B is a vector that comes from this yellow colored subspace, only the column, that means B has no components in the left null space. That means it's fully restricted to the column space of A, then you can solve it. Right? Because there is a vector XR that will get mapped to here, mapped to B. There might be infinitely many number of vectors, but there will only be one XR that gets mapped to B. The infinite other possibilities that come up are essentially additions from the null space. Okay, so this is like the particular solution. All the everything else that gets added are the homogeneous solution. That's from the null space. Okay, but the moment you have a vector B that's here, right, which has a component in the column space and has a component in the left null space, you cannot solve it because there is no X here such that if I take that X and multiply it by A, I'll get this vector because I can never produce a component in the left null space. That means I can never produce this vector B that you've given. That means I cannot solve it. Okay. That's essentially what I've shown here. What I've written down here. You can go through that later. That's A. What if the matrix that we were working with was A transpose instead? What kind of a mapping are we talking about then? So A does this mapping. A maps the row space to the column space, the null space to 0. What kind of a mapping does A transpose do? What do you think? Your intuition is right. What is it? Reverse, correct. Okay. So what will get mapped to what? You're right. It'll be some sort of reversed operation. Sorry. So the arrows will go in the opposite direction. Great. Okay. What will this get? What will this get mapped to? So you're saying this will get mapped to the null space? Well, as long as A transpose, see, it's the same thing. If your original matrix is A transpose, right? Then this is the row space and this is the null space. Then this is the column space and this is the left null space, right? Because the row space is C of A transpose. If you started with A transpose, then C of A is the row space because C of A transpose transpose, which is A. So this gets mapped here. This whole thing gets mapped to 0. You cannot reach this region. That's okay. All right. This is what I wanted to cover, and we'll stop there. We won't proceed. We will now discuss some of the questions you guys had. What was it? It was regarding the assignment, right? What is the problem with the assignment? Yeah. Where are you? What difficulty are you facing? What was not clear? Yeah. Yeah. Okay. How would you derive it? Here. The reason I gave this example is because this kind of at least simplifies or gives you an idea how to go about doing this, right? For example, if phi is 0, right? What will be the relationship between output and input? If phi is 0, my output will be what? What will be the relationship between my output and input? Hey, we talked about this, right? Did you guys look at this? Did you guys go through this or no? Why not? That's the reason I did it in class. It was not recorded. Oh, it was not recorded. Sorry. Yes, it was not recorded. Okay, let's go through. Right. If you have a block, right? II is the intensity of the incident X-ray. What comes, and let's say this is of length L and this has got an absorption coefficient mu, then this is given by. Okay. So I'm asking you, if this has an absorption coefficient mu, if phi is 0, what is the relationship between I naught and II? Well, it's this, what I've written, because the length or the distance that the X-ray would have to travel through this medium is of length L. That means the output would simply be the incident intensity multiplied by e power minus absorption coefficient multiplied by the distance that the X-ray has to travel. What will happen if phi is not equal to 0? Or let's do this. What if when phi is 90? This is yeah. What is it? Yeah, same thing. It will simply be I naught will be. For now, since II, mu are constant, we'll not talk about them. We'll only talk about L. L is the only thing that can change. So if it's incident like this and it's coming out, the length is still L. So we only have to worry about L. Similarly for 180 degrees and 270 degrees. Okay. What if it was not 0? It was some non-zero value. It is not equal to plus or minus 90 or plus or minus 180. What if it's 45? Maybe that's easier. What will L be then? Or L, I should call it L phi, because L is really a function of phi. I'm going to write it like this. What is L phi? When theta is 45. I mean, how would you find out? You at least you tell me that, and then you will try and find out. Where is it entering and where is it leaving when phi is 45? From the top right corner to the bottom left corner, right? Okay. What is the length? What is the distance between those 2 points? Yep. How will you find out? Of course, you maybe you can't say what the distance. How will you find out? Can we find out? Huh? Sorry. Okay. Even with the I've given you phi, right? There will be cos 45. What is cos 45? Let's look at that. What is cos 45? 1 by root 2. So what are you saying? It's L times cos 45, is it? Or it's just cos 45? Is it 1 by root 2 into L? What is root 2? 1.414. That means L divided by a number greater than 1. That means the distance traveled should be less than L. Does it make sense that okay? If you start from here and you come out of here, is the distance that you've traveled greater than L or less than L? Given that the size of the square, the side of the square is L of length L. Is that? Are you saying if I travel from here to here, I travel a shorter distance than if I travel from here to here? This is essentially a question of what is the length of the diagonal of a rectangle or a square. Now, if I have a square, what is the length of the diagonal? Let's say this is of length L, L. No? How would you find that out? Okay, all right. So this is a right angle triangle. So Pythagoras' theorem applies. So the length of the diagonal will be L square. The length of the hypotenuse is the square of the length of the hypotenuse is sum of the squares of the other sides. So it will be L square plus L square, which will be equal to 2L square. That's the square of the length of the hypotenuse. That means the length itself will be root 2 times L. Right? That means you travel a larger, of course, this is the largest distance you will travel in the body. That is when it's 45. Okay. Now, how would we find out for any arbitrary, what we really want is L of phi. We're not interested in just the value of L for specific values of, very specific values of phi. But if you have the general formula for the function for the relationship between L and phi, then I can compute for any phi that I have. If that is the case, the question is, how would you find out that relationship? All right. I won't tell you exactly how to do, but I'll tell you the procedure, right? I don't know what the function will look like off the top of my head, but the way I would do it is I have my square and I have this line. If I want to find out this distance, right? This is the distance I need to find out. That is L of phi. All I would do is I would find the intersection of this line with all these 4 lines. It'll only intersect 2 of those lines away, except for these conditions, right? Where it'll intersect all 4 lines. all of them at the same point, it will intersect. I mean, in fact, sorry, I should not say that. It will intersect all 4 lines all the time. Okay. Only with 2 of these points will the intersection be at the edges. For the other lines, it will be outside these edges. Okay? That's one way to do it. The other way to do it is to use the idea of similar triangles to figure out what this would be, and from this figure out. And if you know this, then you know this, and then from that figure out. So as I said, you essentially have to solve intersection of lines. And then once you have those points, which will be functions of phi, you know the relationship between L and phi. Once you have L and phi, then you simply you know I naught of phi. You know I is fixed. You get e power minus mu L of phi. You substitute for different values of phi. If you take the logarithm on both sides, you'll have I naught of phi divided by I will be equal to minus mu L phi. If you for different values of phi now, you'll get different values on the right hand side and the left hand side. In fact, you only need one because the absorption coefficient is constant. You only need one reading. Once you know one value for L of phi and one value for the left hand side, then you can solve for mu. So here you only need one. But it'll be good to find out this general expression. Once you do that, then copy the other. The other problem had, I can't remember correctly, 4 regions like this. You kind of have to repeat the same procedure. Here we've assumed each one has a different absorption coefficient. And you still have now the X-ray that's passing through. You'll have to solve for the intersection for each of these. In fact, it will pass through the origin. At any given point in time, it will only pass through 2 of these objects. You'll have to find out where it intersects. Each of these 4 regions, and then from that know the points of intersection, and then compute this length and this length, and then you will then get a general expression like this. Minus mu1 L1 phi minus mu2 L2 phi minus mu3 L3 phi minus mu4 L4 phi. You have 4 unknowns. You have an equation like this. You need at least 4 readings to be able to find out what are the 4 absorption coefficients. But in your case, you're not interested in finding the absorption coefficient. You're given the absorption coefficient, and you simply have to find out if I have my X-ray and I change phi, what will be the relationship between the output I naught and phi? That was the question. Your problem was the forward problem, where you know what the material is. You want to know if I give so much X-ray at different directions, what is the output intensity of the X-ray that I will get? Okay, so that's how you do 6. What else? Anything else? This one is it. Okay. I'll have to see what the problem is first. I don't remember. Connectivity matrix graph is set. Okay. What will be the connectivity matrix to start with? What shape will it be? Why 6 cross 6? Sorry? Yeah, there are 6 nodes, so there has to be 6 cross 6. Okay. All right. What will be the first element? let's say if first is this is A, B, C, D, E, F. What can we say about the diagonal elements? Or what is the matrix you got? You would have written it down somewhere, right? Or no? Yeah. Tell me what the elements are. So the diagonal elements, what can we say about the diagonal elements? All zeros. Why? Yeah, because you don't have a loop like this. Okay. Can you read it out? What are the values? 1. Huh? Sorry, you'll have to repeat it again. Plus 2 or 1 now? Ah, yeah. Okay. Sorry. Right. Yeah. All are zeros, eh? Yeah. Okay. 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 Is there no connection between D and C? Yeah. Yes. D and B? Yes. You're right. Okay. Okay. Now is there a path between I and J that goes via another path? How many paths are there between? Is this I and J? Okay. Let's try and find out. How many paths do we have between A and B? Okay. I need to think about this. I and J. Their path goes by another. I J. That means I need to know if this know if this is 1 and hmm, Yeah. Okay. The first one you were able to do. How did you do the first one? Or did you trace in the graph? No, you should not trace in the graph. You should. I mean, the whole point is try and find out algebraic operations that you can do on the matrix matrix to find out. So of course, if you have a graph that has billion elements, you're not going to sit and trace all the billion elements. It's it's not a class in it's not a kindergarten class where you're ask children to trace paths. You should do this using the matrix C. So what is the algebraic operation that you do on the matrix C so that you can find out if I'm interested in uh, going from I to J, I want to know if there is a path from if there is a path from I to J that goes through another node. Okay. See, if you ask, okay, if the question is there a path between nodes A and E that goes through D, right? If that is the question, from the matrix, how will you figure that out? So the question is, you have to go from A to E. The question is, does this path exist? No, no, don't look at the graph. Look at the, you need to tell me that from the matrix. The graph is just for you to verify if the procedure that you've come up with actually works. A to D is 1. Okay. A to D is 1. Okay. What does it mean? When if A to D is 1, well, you'll have to first tell me this. Are the columns, are the rows, do the rows correspond to where you start from? What is the definition? Yeah, rows correspond to where you start from and columns correspond to where you end up. So this is 1. That means you can start from A and go to D. Okay, all right. It's 1. So there is a path, right? Okay. How do we find this out algebraically for any? Well, if you're given I, K, and J, right? You simply have to see if the elements Ci, K and Ckj, both of them are 1. If the product of the two is 1. If the product is non-zero, so product is 0, then it's nothing. Or the sum of the two has to be 2. If it's less than 2, then you know that one of the connections or both the connections don't exist. That means I would say Cik, let's look at the Cik plus Ckj. If this is equal to 2, then I'm fine. Then there is a path, right? So the way I can find out Cik, if you were to take the matrix notation format, right? Then I would see what? Okay. Okay. Transpose. Mm, Transpose. See. If I do this, then that is equal to multiplying the two of them. So this will be Cik multiplied by Cij. If this is equal to 1, then there is a connection. If this is equal to 0, then there is no connection. This is if you have a specific K, right? What if I ask you, I don't care about K? Tell me if there is a path from I to j via one more intermediate path. Then what would you do? When you add, this is when you multiply. Well, simply iterate over all possible k's, right? Go through all k's. So if I do Cik plus Ckj and I find the sum over all k, will that work? What will that, for me to have at least, the question is there a path from I to j that goes through another path? When can I say that there is one? If I do this operation, can I answer question one? What is the condition on this number that I compute for me to answer yes or no for this question? Okay, I'll leave it at that. That's for you to test. What about this? Can we now find out if that is one way to do this? Can we now find out how many paths there are from I to j that go through another path with just one intermediary? Right? You can extend this and ask, well, give me paths from I to j that have two intermediaries. Or if there are paths where I have two stops in the middle. Okay, that's sorry. Yes. So instead of k, it will be I to k1 to k2 to j. Yeah. Okay. Yeah. I'll let you figure the rest of it out. But that's the logic. Anything else? All right.